Hello. Alright, chapter 3. So now we're going back. Chapter 3 is really broken up into two parts. One on matter, which is mainly a review of middle school, though I'm going to throw some new things in there. And I'm also going to throw some of chapter 20 in there. So the first part, matter, is chapter 3. It's actually parts 1 and 2. And then there's a little bit of chapter 20 in there as well. And then the second half of the unit is on energy, and that includes things like specific heat. But if you're going to talk about temperature change in an object with energy, then you should also talk about melting and boiling and freezing. So we're going to throw a little bit of chapter 17 in there as well. So for this video, I'm going to talk about the difference between mixtures and compounds, a little bit about phase versus interface, and then finally dissolving and how a solute and solvent combine together to make a solution. All right, first of all, a mixture is a physical combination, not a chemical combination of two materials. So what is the difference then between the two, and how do you make them? How are they different from compounds? Well, I would stop and write this note down. When you're making a mixture, what you're doing is you're making a physical combination. So painting a car red, for instance, you use a spray paint, you spray the paint onto the metal body, and you're creating a mixture. And so you're using a physical way to bring these two things together. That's not to say that in chemistry, when we run chemical reactions, we don't stir or we don't heat or try to blend things. We certainly do. But for a mixture, again, that sort of combination is the only way things can come together. Whereas with chemicals, you have decomposition and synthesis and combustion and all these different types of ways of bringing things together chemically. So there's really not too much of a difference between a mixture and a compound. They are both attracted in terms of Coulomb's law. So again, force equals K, Q1, Q2 over D squared. The difference is the force of attraction is not very strong. If you paint a car red, are the positive protons in the paint attracted to the negative electrons on the metal car body? And the answer is absolutely yes. Are the positive protons in the metal body attracted to the negative electrons on the red paint? And the answer is yes. But all the red paint's going to do is stick to the surface of the metal. It's not going to create a attraction strong enough that you create a chemical bond. In other words, you're not creating radium chloride. You're just painting the car red. And this can easily be removed, the paint, simply by scraping it. You can't scrape the hydrogen off of oxygen in order to break apart a water molecule. So yes, mixtures come together by Coulombic attraction. Compounds come together by Coulombic attraction, but compounds have a much stronger Coulombic attraction. There are two types of mixtures. One heterogeneous, the other homogeneous. So this should be pretty much a review of middle school. In a heterogeneous mixture, we can see the substances that make up the mixture. We can see that they're not evenly distributed. If we were to take samples, we might get different percentages of materials. For instance, if we had a jar full of coins, and we reach our hand in and pick out 5, we might pull out 4 pennies and a nickel one time, and then another time we might pick out 3/4 a dime and a penny. So the samples are going to vary from sample to sample, and with a heterogeneous mixture, it's easy to separate the components. Like I said, you can't scrape the hydrogen off of oxygen in a water molecule. Homogeneous mixtures, again, they are not strongly attracted to each other, but they're strong enough so that the distribution among the solute and the solvent is an even distribution. In other words, it looks like it's one material. A good example would be if you dissolve salt in water, or nitrogen, oxygen, carbon dioxide. All the gases in our atmosphere are a homogeneous solution of gases. We can't see the different components, but they are a lot easier to separate than chemical compounds. All right, separation techniques. Sorting. If we have a salad, we can pick out the tomatoes. You can actually do this in crystallography too. Louis Pasteur was working on crystals, and he was able to pick out and separate different types of crystals from the wine that he was working with. So anyway, you can actually sort on a much smaller scale, but I always use tomatoes in a salad as an example. Filtering. We are going to use a semi-permeable membrane, and that's going to allow the liquid to pass through, but we're going to collect the solid inside the filter paper. Distillation would be when you have a mixture of liquids and you boil them, and the one with the lower boiling point boils off first, leaving behind the one with the higher boiling point. Difficult, more chemical processes would involve things like electrolysis. Electrolysis would mean, hey, let's take chemical A and chemical B and zap them with electricity and see what happens. Hydrolysis, which means use water. And pyrolysis, so we're going to use heat. Pyrolysis stands for fire, but we're going to use heat. These things are going to cause chemical changes. They can also cause physical changes, but generally when we talk about separating one thing from another, electrolysis is not an easy way to separate things. We could zap water with electricity, and that will separate the water into hydrogen and oxygen gas, but that is not an easy thing to do. All right, solution. We want to talk about solute versus solvent, and what is the dissolving process from chapter 20. Okay. A solution is another name for a homogeneous mixture, so we have an even distribution. The solute, this is a review of earlier, so you can take notes, but I'm not going to write them. The solute is the thing that gets dissolved, and the solvent is the thing that does the dissolving. And again, usually we use water as the solvent, but there are certainly many other different types of solvents other than water. All right, the dissolving process. First thing, this is according to your book, we have to take the solute and solvent and pour them together. 2, when you do that, that breaks apart some of the solid crystal. Now, they're talking specifically about your solute being a solid and your solvent being water. So they're using one specific example. Now, I hate this step number 2 because I think it confuses students. Yes, when you pour the salt into the water, it will break apart some of the crystals, but this is a very, very minor step. There's only a little tiny bit of breaking apart of the crystal that goes on just by pouring it into the solvent. The big thing is this step right here, number 3. Solute and solvent have to interact with each other. So in other words, the solvent has a job to do. And I think I showed this earlier in the course, but I'm going to show it again. In fact, I know I showed it earlier in the course. We have sodium and we have chloride. And if we're making a three-dimensional crystal out of it, then the particles might alternate like this. Okay. And we said water has a job to do here. Water molecules are what we call polar molecules, which means that if we have a water molecule, we have one distinctive positive end and one distinctive negative end. Now, just because we have positive and negative oxidation numbers doesn't mean that all molecules are polar. We'll study that in chapter 12 and in chapter 14, which is the unit after this unit. All right, so water has a job to do. We can get the negative end of a water molecule to line up with the positive, and then that will attract this particle and pull it out. Or, here's another water molecule doing the same thing, right? H2O, positive, negative, pulls out that sodium. Or, we can get something like this, right? The positive end attracts the negative chlorine and pulls that out. So, ultimately, the water molecules have a job to do where they are going to separate from each other the positive end is going to pull out a negative part of the crystal, and the negative end is going to pull out a positive part of the crystal, and what that does is that breaks down the crystal and gets all the particles to separate. So this interaction is something called solvolysis. Fourth thing, random particle motion will cause the solute to spread out in the solvent. Okay. Sometimes called Brownian motion, this random particle motion. Alright, so that's the baby version. Here's the big person version that you should learn. Really three things that happen here. Solute expands, solvent expands, sphere of hydration. Alright, what we mean by the solute expands is that the particles separate. That requires heat. Now the heat doesn't mean you have to heat it on a hot plate. The heat could come from the energy of the materials that are already there. The heat could come from the thermal environment. The solvent particles have to expand and separate from each other. This also requires heat. And then in the third step, we get what's called a sphere of hydration, which is what I showed you in the last part where the water molecules are surrounded by positive and negative particles. This sphere of hydration releases heat. And we call the entire three-step process the heat of solution. So we would take the change in heat, let's call it delta H for step 1, the change in heat for step 2, delta H for step 2, and the change in heat for step 3, and add them all up together, and that would give us the heat of the solution. So you really have two things here when things dissolve, two possible options. Back to our little sphere of hydration. Okay, let's take a look at this. Some things that dissolve are what we call exothermic. And we talked about this earlier in the course. If it's exothermic, that means it releases heat. The process releases heat, and our delta H value comes out to be some sort of negative value. So here in step 1, we're taking the solvent particles and we are expanding them, so we expect the delta H for step 1 to be some sort of positive value. So in other words, from here to here, this requires heat. So we start with low energy, we raise it to higher energy. And then for step 2, we have to take the solute and separate those particles. Again, that requires heat. So our energy levels are going up again. Now in the third step, it releases heat. So delta H for the third step is going to be some sort of negative value. If it is a large negative value, we go from something that is very unstable to something that is very stable. This releases a tremendous amount of heat, and we would say that the overall net process, if we look at the beginning and the end, this would represent how much heat is released, what we call the heat of solution. Now, not all things when they dissolve release heat. In fact, most solids, when they dissolve in water, actually absorb heat, which means you have this situation where, again, you have delta H for step 1 and step 2, the expansion of the solvent and the solute require energy, so we're going to use positive values. However, in step 3, you only get a little bit of energy back, so this is a small negative value. So in this case, the overall process, we'll call it again heat of solution, is actually some sort of positive value, what we call an endothermic process. Okay, so a couple of things here. Most of the time, although there are exceptions, so I'm going to put a little star here, most of the time, if you take a solid and dissolve it in water and you get a solution from it, the delta H is going to be positive. Usually requires heat to do that. If you take a gas, however, and dissolve it in water, and it creates a solution, then delta H should be negative. All right, so different types of mixtures we'll talk about. Let's talk about it right now. What is the difference between a suspension, a colloid, and a solution? Glad you asked. Pardon me, I'm sorry. Solutions are homogeneous, where suspension and colloids are heterogeneous. And what is the Tyndall effect? The Tyndall effect is a way of determining whether something is a suspension or a colloid. And this all comes from chapter 20, part 1. All right, suspension. You can see the components in a suspension. Now, you can shake it like certain medicines are suspensions, things like antibiotics are suspensions. You could shake them before you administer the medicine, and they will temporarily appear to be suspended in one another. But if you let them sit, they will separate back out again. So suspensions are things where you can see the components. If you mix it, however, it will temporarily appear to be homogeneous, but given time, it will separate back out. Good example of a suspension is milk. Now, milk is pasteurized and homogenized so that it stays as one unit longer, but if you allow milk to sit, eventually the water will separate from the animal fat. A colloid. All right, a colloid is heterogeneous, but it looks like it's homogeneous. The particles are so small in the solute that you can't see them, but if you shine light on them, then they become apparent. Good example of something that is colloid-like would be, for instance, dust. If you're walking around your room, it doesn't appear to be dusty, but then when you see that beam of light come shining in through the window, you can see the dust there, and that would be a good example of what's called the Tyndall effect, where the particles are small, you can't see them unaided, but they do reflect light, and they become visible once you're reflecting that light. So really, it's a matter of how big the particles are. And these particles represent the solute. So if the solute particles are big enough to be seen, then we're dealing with a suspension. If they're too small to be seen, but can be seen by shining light, so we'll write light reflection for that, then they are a colloid. Now, you do not have to know these size numbers. A homogeneous solution, a pure solution, still has tiny little particles of the solute in it, but they're so small that they cannot be seen, and they do not reflect light enough to be able for us to see the reflection. So there would be an example of the Tyndall effect. Again, at the top of the solution where there's no light, we're not seeing anything as far as particles, but where we shine the light, now we're seeing the particles as the light reflects off of them. All right, so what's the difference between phase and interface? That didn't come up. Actually, I think it comes up in another video. So I'm going to stop right here. We will pick up the next video with saturated, unsaturated, and supersaturated solutions. Thank you.